Section 1.3, New Functions from Old Functions. In this section, we start with the basic functions we discussed in Section 1.2 and obtain new functions by shifting, stretching, and reflecting their graphs. We also show how to combine pairs of functions by the standard arithmetic operations and by composition. Transformations of functions. By applying certain transformations to the graph of a given function, we can obtain the graphs of certain related functions. This will give us the ability to sketch the graphs of many functions quickly by hand. It will also enable us to write equations for given graphs. Let's first consider translations. If c is a positive number, then the graph of y equals f of x plus c is just the graph of y equals f of x shifted upward a distance of c units, because each y coordinate is increased by the same number c. Likewise, if g of x is equal to f of x minus c, where c is greater than 0, then the value of g at x is the same as the value of f at x minus c, which is c units to the left of x. Therefore, the graph of y equals f of x minus c is just the graph of y equals f of x shifted c units to the right. We can see this in figure 1 here. So, here are the vertical and horizontal shifts. Now suppose c is greater than 0. To obtain the graph of y equals f of x plus c, we shift the graph of y equals f of x a distance c units upward. Y equals f of x minus c, we shift the graph of y equals f of x a distance c units downward. Y equals f of x minus c, shift the graph of y equals f of x a distance c units to the right. And y equals f of x plus c, we shift the graph of y equals f of x a distance c units to the left. So here's our graph. So this is our function y equals f of x. So if we want to shift it up, then we can see it's f of x plus c. If we shift this graph down, it's f of x minus c. If we want to shift this to the right, it's going to be f of x minus c. And the reason is because if we set x minus c equal to 0, and solving for x would give us plus c. That's why we're moving to the right. And then over here, we're going to move to the left, because if we take x plus c and set it equal to 0, it's going to equal negative c. So we're moving it to the left c units. Now let's consider the stretching and reflecting transformations. If c is greater than 1, then the graph of y equals c, which is a constant, times the function f of x is the graph of y equals f of x stretched by a factor of c in the vertical direction, because the y coordinate is multiplied by the same number c. The graph of y equals negative f of x is the graph of y equals f of x reflected about the x-axis, because the point xy is replaced by the point x negative y. So let's see figure 2 and follow the chart where the results of other stretching, shrinking, and reflecting transformation are also given. So let's take a look here. So we have, let me move this up here so we can see this a little bit clearer. Okay, so to your right here, the vertical and horizontal stretching and reflecting. So when y is equal to a constant times f of x, we stretch the factor of y equals f of x vertically by a factor of x. So we can see here, this is the regular form, and we stretch it if c is greater than 1. Now, if the constant is a fraction, which is being multiplied by 1 over c, f of x, then we're going to shrink the graph of y equals f of x vertically by a factor of c. So that means we're shrinking it, so it's shrinking down. Now, if we take the constant and multiply by the input, which is f of cx, then we shrink the graph of f of x horizontally by a factor of c. If we have f of x over c, which is 1 over c times x, then we stretch the graph of y equals f of x horizontally by a factor of c. If we have y, which is equal to negative times the function f of x, then reflect the graph of y equals f of x about the x-axis. So we reflect it here. And then y equals f of negative x reflect the graph of y equals f of x about the y-axis. So adding another example here, we have the figure 3, which is going to illustrate these stretching transformations when applied to the cosine function with c is equal to 2. So for instance, in order to get the graph of y equals 2 times the cosine of x, we multiply the y-coordinate of each point on the graph of y is equal to cosine of x by 2. This means that the graph of y equals cosine of x gets stretched vertically by a factor of 2. So if we take a look at our regular cosine function, which is in purple, if we multiply it by 2, meaning if we multiply it by a constant, then that means we're stretching it vertically. So you can see that the blue graph is stretching vertically. Now, if we take a constant, which is a fraction, so you have 1 over 2 times the function, then it's going to shrink vertically. So therefore, the green is shrinking vertically. Now, if we take, again, the purple tells us that y equals cosine of x. If we multiply x by a constant of 2, then it means we're going to shrink horizontally. So the graph is in blue is shrinking horizontally. Whereas if we take 1/2 and multiply it by x, then we're going to stretch the graph horizontally by a factor of that constant.